All right, shall we continue?
Yeah, sure.
Okay, I am going to reverse myself a little bit here. We had a discussion before the break whether or not the dx should be incorporated there. There is a dirty little trick in statistics that if you run into a little bit of trouble with your units, so of course, if I want to calculate the probability, the answer has to be unitless. So in that case, the dx should be there. But if you run into a little bit of trouble with that, and then you just call it a likelihood, and then you can then you have a likelihood that is proportional to the probability, but you can fantasize your own units with it. So for the coming slides, I did not include the dx, so I just removed it here again as well. It now means that, and this is just repeating the last slide again, that this likelihood has units per meter now. And that, and you saw the preview, of course, already, that because we said that this scattering event, this one scattering event could take place everywhere along this line, we had to integrate. And by integrating, we actually do add the length in here, the dz in here. So then in the end, what we calculate here is indeed a total probability. This one is unitless as we should expect. So one little remark, I've used the integration variable dz1 here. So z is the distance along the line. So dz1 is then an elemental length along that line that indicates where the first scattering event takes place. That's why there is a subscript n. But of course, since this is just part of the path length, we can also say that this dz1 is equivalent or has the same length as a unit, as a elemental path length, dl, along this line. Okay, but now I want to look at the situation where we have two scattering events. So again, what we're going to do is split this trajectory into sub-events. So a propagation of an interaction-free propagation to scatter site number 1, then a scattering event there, then interaction-free propagation to scatter site number 2, an interaction there, and then a scatter-free propagation to the end. So let's look at then again the likelihood for this particular path has the familiar ingredients. It has a propagation over length L1, scattering event at 1, then propagation over length L2, then the second event, and then a propagation over the segment L3 in which nothing happens. So this is then again the likelihood of this path happening, and because of the dimensions, this one has then the dimension of per meter squared, per square meter, if you like. Here too, we can just group the exponential terms together because L1 plus L2 plus L3 is simply just total length L. So the exponential term just comes in front. And then what is left of this equation is 2 times a factor of mu s. Now here too, we have to take into account that this was only one of the possible options in which we could have a path with 2 scattering events. And if we look close, then we see that the second, sounds a little bit strange to start with the second scattering event, but the second scattering event can occur anywhere along this line. It could occur immediately, it could occur only at the very last part, or anywhere in between. It can occur anywhere. But the first scattering event, because it's the first, can only occur up to the second one. So it always has to be on the left of the second one. So if we want to add all these possibilities together, that means that we have to we can vary the first scattering event up to the location of the second scattering event, and the second scattering event is then can then take place anywhere between 0 and L. So we get this kind of double integral. We have to add all these possibilities together. But again, the first scattering event can only occur up to the second scattering event. Of course, these are again integrals over Z1 and Z2 in this case, so that are the segments of where the first or the second scattering event can occur, and everything that is in front of this integral just behaves as a constant as far as the integral is concerned. So we can first calculate the integral from 0 to Z2 of Z1. That gives us a vector Z2 simply, and that then we have to integrate from 0 to L. So that gives a vector half L squared. That half L squared can be combined with this mu s squared that we already had. So the final expression for the probability of having propagation over the length L with two scattering events happening, adding them all together is going to be this last expression. So mu s times L squared divided by 2 times an exponential minus mu s times L. Yeah, is this clear enough?
I think so, at least for me.
Okay. Well then, yeah, and again, just to keep the bookkeeping a little bit nice, we these are of course integrals over for each of the events over the whole length, but what is implied is that that these steps are small steps, but they are equal to some value dl. Okay, well, this one you see coming, of course. So what happens if we now look at 3 events? Well, the reasoning is the same then. The third event can occur anywhere along the line between 0 and L. The second event can only occur from 0 up until the third, and the first event can only occur up until the second. So again, so I'm speeding things up a little bit. So we, in principle, we should just write this likelihood again as an interaction-free propagation over L1 times mu s times interaction-free propagation over L2, etc. But we can group all these segments together, these exponentials. So we get the exponential term here in front, and then because we now have 3 events, we get 3 times a factor of mu s, and that also means that the units of this likelihood are going to be per meter to the third power. Okay, so for n is 3, well then the total probability is going to look like this integral. It's the concept is the same as before. So we have an integral over of Z1 that can run up until Z2, and then one integral that's inside an integral over Z2 that can run up until location Z3, and then the outer integral is 3. Then the outer integral runs from 0 to L. So starting from the inside out, we can work this integral. So first will give us a factor of Z2, and then we'll get a factor of half Z etc. You get the idea. So in the end, multiplying everything out becomes mu s times L to the third power divided by 6, 2 times 3, and then exponential minus mu s times L. Now we can generalize this, of course. We can now you see it occurring, but we can now do it for n scattering events as well. So not 3, 4, 5, n. What do you expect if you just look at how these equations are developing? Or can you speculate how the expression for n forward scattering events would look like?
Yeah, I'd say mu s times L to the power of n over n factorial times the exponential.
Yeah, that's exactly right. This is then what the result is going to be. So this is the general case for n scattering events. And again, caveat that that all these integration variables, these segments are supposed to be the same. Are supposed to be the same size. Okay, so this was propagation along a line with well, let's say any events. So we can look at these so just to see how these curves look like. I've plotted a few of them there. So if we would now look at all photons that travel a length L, and we don't really care how many scattering events they undergo. What we can do is that, for example, we can inspect that after about a length of 2 millimeters, most of the photons will have scattered. In this case, for this example, will have scattered two or 1 or 2 times. If we go further at a longer length, then we see that they have scattered, likely scattered more often. So that that kind of makes sense. But the derivation up until now assumed that that this event just happened, but we were in the end we were interested in a reflection signal. So to make this model a little bit more complete, we have to actually include a probability that the scattering is actually in the forward direction in this formalism. So where we had all these, so we had these propagator steps in which nothing happened, where the photon just propagated, and then we had the term µs each time a scattering event occurred. But now we want to refine that into not only the probability that the scattering event occurs, but also that that event is in the forward direction. So we have to include this factor PF, and of course that is going to be included anytime this scattering event occurs. So it is going to be included within this power term. Yeah. Okay. And the caveats. All right, but now let's look at this actual geometry. So what we're assuming is that we have this fiber that is in contact with the tissue, and we're only looking at photons that propagate along, let's say, the black dotted line. They can have an arbitrary number of events in the forward direction, but they will have only one backscatter event. So we can make build a general expression for that case, and we can also realize that statistically it does not really matter if this backscattering events is the first one that happens, and after that there are n forward events, or first there are n forward events and then is the backscatter event, or half of the n events takes place, then a backscatter, and then the other half of the forward scattering events. That does not matter. So we can really generally just include an extra term here. So this is the PB is the probability of backscattering. µs is the probability of this scattering event happening, and that backscatter event again can take place anywhere along now this line from 0 to infinity deep. Also there for the total signal, so the total signal with one backscatter event and an arbitrary number of forward scattering events, we have to integrate that over the length of this black dotted line, because the backscatter event can take place anywhere. Now I run into a little bit of a problem with my bookkeeping, because if I would follow the same definitions as before, then my DZB, so the step over which I move this backscatter event, would be equal to a DL, just like the DL that we had before. Problem is that if I 1 second. Somebody sent a chat, but somehow I lost my chat window, so I have to try to find that back. Not sure where that went. Oh, there it is. Oh, ho, 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 ho. Was it actually a chat that was aimed at me, or was it?
Yeah, the question was, shouldn't we also check that all the scattering events are normalized?
Yeah, that in principle you're right. That's how you should do it. But if you do that, you'll find that actually this in this case it is this works. No, that's not entirely true. No, that's not entirely true. Because once we include this PF that can take any value, then it is not necessarily then it is not then it is not longer normalized. Then it just calculates the fraction of photons that is actually forward scattered. And it's the thing that should be normalized is when you add all the photons together, so the ones that are forward scattered and backward scattered, then the probability should be completely normalized. So in this case, it's not it doesn't have to be anymore. So if I would propagate the photon from the source fiber back to the detection fiber along this line, then the total length would be 2 times the ZB. If ZB is the location of the backscatter event, the photon goes back and forth, then the total length should be will be 2 times ZB, which gives me a conflicting statement that this element dZB is only half of the segments of DL. So if I would do that. If I would use this expression as it is, then I would have an integration range of integration variable of L over 2, which would not give me the same result. So it's a little bit hand waving, but I'm just going to smuggle in this factor 2 here so that I can use a DL here for this integral that is the same as the dz1 and the dz2 and the dz3 that I used in the integrals that are actually living under this term. So it's a little bit hand waving, but otherwise the math really does not work out. So let's see if we can work with this equation. So we have to add. If we want to have the signal now, so the total signal that we would detect if we only look at photons that have been backscattered once and an arbitrary number of times in the forward direction, that means that again, according to the recipe, we have to add all these possible number of forward scattering events. So within the integral, now comes this sum over n is 0 to infinity events in the forward direction that we all have to add up together. So once we solve this integral or this expression, if we can solve that, then we have our basically calculated the probability that we detect photons that have been backscattered only once and an arbitrary number of times in the forward direction, and that we will then use as our estimation of the signal. So we can first fill in the expression that we found for in the previous slides for the propagation along L with only forward scattering events. So PF is now in here as well. And now basically to solve this, we can go 2 routes that are equivalent. We can do first the summation and then the integration, but we can also do the integration first and then the summation to solve this, and it should give the same result. And luckily it does. So let's start with this one. So first the summation and then the integration. So that means that we take the expression as it is, and if we take a close look to how this sum actually looks like, we see that it has this kind of form, this kind of terms. So it's the form of x to the power n divided by n faculty. This is, I think, a geometric series, if I'm correct, and that evaluates to the exponential of x. So we can immediately substitute this term here, this sum term here, with an exponential of this argument. So like this. Then we can juggle a little bit with the pluses and the minuses. So if we make this, if we rearrange this a little bit, we can write it as one as minus mu s times 1 minus pf times L. Now to solve this integral, we can make a substitution. We can substitute L prime as equal to L times 1 minus pf, adjust the integration boundaries. In this case, that is not really necessary because from 0 to infinity it just stays from 0 to infinity. And then rearrange the equation. So we get a prefactor here that is given by the backscatter probability divided by 1 minus the forward scattering probability. And then this remaining integral term. So can you now immediately say what we will end up with? Without calculating the integral, just by.
So this should be the mean free path length without scattering, right?
Almost,
so it would be one over mu.
No, almost. The L is not in here, so
okay.
this is just mu s. This was just simply the probability density function for path length again, and the normalized version. So this whole integral evaluates to 1. So the final result is this. After all this work, is this simple expression. So this again, this is the signal that we would expect if we detect photons that are backscattered only once and forward scattered any arbitrary number of times. And it is only a function of the probabilities of forward scattering and the probabilities of backward scattering. So the whole scattering coefficient itself has dropped out completely. It's an interesting result, isn't it? Of course, just to check, we could do it the other way around as well. We could do the integration first and then the summation. That is that is also not that complicated. So we can rearrange that a little bit to have the summation out and the integral within. This one too, this integral too, we can inspect, and we can also see that this has a standard form. First we do a substitution. L prime is mu s times L, so basically making it dimensionless. And then this integral L prime to the power n times this times the exponential also has a standard form, and that evaluates, if you look in the integral tables, that evaluates to n factorial. So can make that substitution too. Then of course this factorial term that is already in there will cancel with the newly obtained factorial term, and this is then the result for that. So the probability is PB times this sum. This is also a standard sum. It will not surprise you that this one then evaluates to 1 over 1 minus x. So finally, the same result. The same result is found again. So backscatter probability divided by 1 minus the forward scatter probability.
I have a question.
Of course.
Because so in the third line of the PB equals 1, you use the fact that x to the power of n multiplied with e to the power of minus x dx, that is a certain summation, but we do not have x to the power of n multiplied with the exponential of minus x times dx. We have the mu s in there, right? So then we may have to define a new variable in order to make it work, or?
I think the mu s is a typo in this third line.
This one shouldn't be here, I think.
Sorry?
This one should.
Okay. Oh, okay.
Yeah.
Yeah. Okay. I had a problem with that one, but then it's all right if you did.
I think I forgot to.
Thanks.
Yeah. Very sharp. Very good. Very good. So what? So yeah. So what we see that so if you now look at this first look at this intermediate result here, so this is actually quite a simple expression. So the signal contribution that contains paths with only one backscatter event and n forward scattering events is of course proportional to the probability of backscattering, and also kind of makes sense that it is proportional to the forward scattering probability to the power of n, because we have these n events. It also means that for each higher order of n, its contribution, because the PF, the probability of forward scatter, is a number smaller than 1, that contribution decreases with the factor PF. So if you have if you would have a tissue where the PF itself is not that high, so moderately forward scattering tissue, then only the lower orders of n will contribute. So the photons that you will detect will have not been scattered that often. Is then a conclusion from that. Now we can try to give a physical interpretation to this forward and backward scatter probability. So if you look at at what actually happens in this fiber, is because it has a finite size and it has a certain refractive index profile. Not all light that hits the fiber will actually be guided through the fiber. And that effect is given by the so-called numerical aperture, which is defined as the sine of the acceptance angle. So only light that hits the fiber with an angle less or equal to this acceptance angle will actually be guided in the fiber, and the rest will not be guided to the detector. So one way of looking at this. Looking then at these forward and backward scatter probabilities is to assume that only photons that actually scatter within this angular range are detected, and the other ones will not be. So in that case, you could, for example, then define your forward scatter probability as the part of the phase function that contains angles less than the up to the acceptance angle in the forward direction, and you could also do the same kind of evaluation in the backward direction. So that would give you some kind of physical connection of these backscatter, forward scatter and backscatter probabilities in terms of the actual phase function that you would have. Well, we can look a little bit closer then. So we had this intermediate result at some point. So the integral is still there. Again, describes the probability of the signal of detection of photons with only the one backscatter event. But as you can also see, this integral runs over L. So it is a function somewhere in here that runs over L. So that means that whatever is in the integral is actually the path length distribution. So that means that we can isolate from that the path length distribution of photons that have been backscattered only once. So if you then compare these two equations and combine the terms, then you would end up with this expression here in green. And if you really want to make this a true probability density function of path lengths, then you have to normalize it. So that means calculating the integral and then making sure the answer is 1. So that would give this expression. And once you have that, you can calculate again your moments of this distribution. For example, the average path length you can now calculate, and that evaluates to 1 over μs times 1 minus PF as the average path length of these photons that have been backscattered only once. That also means that that you can estimate the average depth that the photons have reached as half of that path length. So 1 over 2 times μs times 1 over PF. So it gives you a little bit of an idea how deep this technique actually measures. Like that. So that is up until now we neglected absorption. So it would be, of course, if our aim is to actually measure absorption spectra, then it would be a good idea to see if we can include that in the model as well. In this case, if we don't include it and we analyze the semi-infinite medium, so it is infinitely deep and infinitely wide, there is only one boundary where the fiber is placed, then there is actually no loss mechanism. So all the photons that are injected must eventually escape again from that medium because they cannot, they're not absorbed, so they must escape. So what we calculated now basically is just a fraction of the escape photons, and that is all of them. So all of them escape in the end, but this is then just a fraction that is actually captured by the fiber. But now, if there is a loss mechanism, so if there is absorption, then we have to include that. We can do that in the same way as we calculated, as we included the forward scattering probability. Because now let's suppose that that when there is an interaction, it is either an absorption event or a scattering event. Then the probability, so if an event occurs, it is either absorption or scattering, and the probability that it is a scattering event is then given by the ratio of the probability of scattering event divided by the probability of both of them. So if something is happening, if there is an interaction, then this alpha, this so-called albedo, tells us what the probability is that it is actually scattering that occurs, and not absorption. So we can include that as well in the same way. So because the signal described the scattering contribution, we can just weight the forward scattering probability and the backscatter probability with by including this alpha factor, and then calculate in the same way calculate a new expression. So now what has changed now is that we now have in the case where we had no absorption, the result did not depend on the scattering coefficient as well. That dropped out, so it depended only on the PB and PF factors. But once we include absorption, the possibility of absorption, then both the absorption coefficient and the scattering coefficient appear in the formula and through this albedo. So this is of course a more realistic form of the model, and that also means that the average depth at which we look at which we measure is also scaled a little bit down. So if you have more absorption, you look a little less deep. All right. So the summary of this part basically is that by taking this probabilistic approach, by following this recipe, we could actually build some kind of a model for this geometry, for this detection geometry. It had a couple of assumptions, of course. The assumption was that the photons were backscattered only once, and that the propagation takes place, let's say, in one dimension on a line. So it is not entirely realistic, but still it gave a workable expression for the signal. Okay, I'm now again I'm a little bit ahead of time, so I propose a break until past, and then after that I have a couple of more slides on Monte Carlo simulations. So let's resume at half.